Thanks, hi everyone. So what I would like to do in this last talk is talk a bit about the chromatic perspective on organizing homotopy groups and how that interacts with what I've been telling you so far, mostly the Goodwillie Tower. There's of course a lot to say about this, so there is no way I can do it justice, but I'll try to give you at least an overview. So since this is a course, I do feel obliged to tell you what BN periodic homotopy groups actually are, so I'll spend some time defining those. So let me start by doing this in the context of stable homotopy theory. So I'll do it for, oh, that's not a pen. I'll do it for spectra first. But the way I'll set it up, it will apply almost verbatim to verbatim, I guess, to spaces. Okay, so, and before I forget to say it, I'll always be working P locally, so everything is localized at a prime. But for today, I'll mostly not care very much what the prime is. So this is not specific to PS2 or anything. Okay, so what we started out with was rational homotopy theory, and really the chromatic perspective views rational homotopy theory as the very first, or maybe the 0th step in a filtration of, or a hierarchy of localizations, if you will. So rational homotopy theory is really step 0 in an inductive process. So rational homotopy groups, let's say of spectra, well, what are they? Well, of course, you get, you consider the usual homotopy groups. So you consider homotopy classes of maps from the sphere spectrum, or maybe some shift of the sphere spectrum into a given spectrum E, and then what you do, invert P, right? So you invert the action, one way to say it, action of the self map of degree P on the sphere spectrum, right? This self map acts by precomposition on this set of homotopy classes, and if I invert that action, I get the rational homotopy groups. I'm already P localized, so the only thing I have to do is invert P. All right, fair enough. So that's rational homotopy theory. But what do you do once you're done with that? How do you move on from there? Well, somehow the complementary information to rational information is P torsion information. So you want to consider the P torsion. So, well, one way to talk about the P torsion is to look at the mod P homotopy groups. What does that mean? You take the cofiber of multiplication by P. So I'll just write that SK mod P. So it's the mod P Moore spectrum in dimension K. And you consider homotopy classes of maps from the Moore spectrum to your spectrum E. And these homotopy classes are usually denoted homotopy groups, and the indexing, I believe, should put K plus 1 over here. It's not so important. So these are often written as the homotopy groups with mod P coefficients because they fit in a long exact sequence with the usual homotopy groups, and there's a multiplication by P map, et cetera, et cetera. Okay, so all right, so that's sort of the information that you've ditched by going to rational homotopy theory. So this is the remainder somehow. This sees the rest. But of course, calculating these homotopy groups is still very hard, right? This is more or less on par with calculating the usual homotopy groups. But the point is, there's a map you can invert as before that will make your life a lot easier. So this is the story of the Adams map. So you consider the Adams map, although Haynes-Miller has insisted that this map is really apparently due to Barrett, so maybe I should call it the Barrett map. Anyway, it became famous from Adams's J of X4 paper, I guess. So this is a map. It's a self-map of the mod P Moore spectrum, but now it includes a degree shift. So it's really a map that goes from some suspension of the mod P Moore spectrum to itself. And this specific integer D is actually 2P minus 1 if P happened to be odd, and you have to take it to be 8 and P is 2. So as usual, P is 2 is slightly anomalous. And the whole point about this map, the reason that it's interesting, or one of the reasons that it's interesting, is that it's not nilpotent, okay? So by that, I mean, you can start composing this map with itself, where you have to suspend appropriately to make the domain and the codomain match up, but you can start composing this map with itself, and you'll never get a null homotopic map. And the reason for that, and this was recognized by Adams, is that this map induces an isomorphism in K theory. So let me give this map a name. I'll just call it little v for today. I guess alpha is maybe more standard, but The point is, so V induces an isomorphism in topological K theory, just complex K theory. Okay, so really what it does, if you look on K theory, it just multiplies by the appropriate power of the Bott class. So in some sense, I mean, K theory, of course, K theory of anything is periodic. It's a periodic cohomology theory. But in this particular case, when you're looking at the K theory of the Moore spectrum, this Bott periodicity really has sort of a geometric realization. There's really a map that implements multiplication by the Bott class, or a power of the Bott class. So you can somehow think of this as some geometric manifestation of Bott periodicity. But the point is, okay, so we have this non-nilpotent map, we can invert it. So you can do the following. Let me do this on another page. You can form what are called the V1 periodic mod P homotopy groups. Right, so what do you do? Well, I'll use the following notation: V1 inverse pi star E Z mod P. Well, it is what I said in words. You do the following procedure. You take these homotopy groups of E with mod P coefficients. So those are homotopy classes of maps out of the Moore space. So this V1, or V, sorry, I'm writing V1 already. Let's call it, this is a V. So V acts by precomposition on those homotopy classes, so I can invert that action. And those are by definition the V1 periodic homotopy groups. Okay, so if you've never seen this before, this seems like a rather wild procedure. I mean, I took something complicated and apparently complicated it even more, but that's not the case at all. Actually, these groups tend to be quite computable. I mean, it's not as easy as rational homotopy theory, but this is something that people, many people, like including Mahold, Adams, worked hard on, and we really understand a lot about these groups. So this really simplifies the problem. Okay, so that's step one. What do you do next? Well, let's say that you understood these V1 periodic homotopy groups, say for the sphere spectrum. Then, well, what's the information that you've destroyed by inverting V1? Of course, it's the V1 torsion. So now you want to do the same thing. You consider the V1 torsion. So you're going to look at homotopy classes of maps out of the cofiber of V1 into E. Again, that's a difficult problem, and you start looking for a self-map that you can invert. So you find a self-map that's not nilpotent from some suspension of V1 to itself. Again, I'm mixing up the notation between V1 and V. This is really just this V again, but all right. Okay, some suspension, different degree. You find some self-map, which is called a V2 self-map. You invert that, and you continue like this. So this is really the beginning of an infinite hierarchy of portions of the homotopy groups that you can consider. So let me try to explain this a bit more systematically in the language of type n complexes and Vn self-maps. Okay, so the general principle here is the following. Let me introduce a few definitions. All right, so first of all, I'll need the notion of a type n complex, or a type n space. So let's say a finite spectrum V is of type n if, well, it's a condition in terms of the Moravec K theories. So if you look at the ith Moravec K theory of V, and this is supposed to be 0 for I less than n, and non-trivial for I is equal to n. Okay, so as I said, this Ki, this is the ith Moravec K theory. If you're aware of those, then great. If you're not, the first few examples are K0, usually just defined to be rational homology. K1 is also a familiar thing, and that's maybe why these things are called K theories to begin with. For the purposes of this talk, you could just take K1 to be K theory mod P, okay, just topological K theory mod P. And then, well, this continues. There's one for every n, but this is already, at least in geometric terms, this is a bit more mysterious. It's harder to describe. if you're completely unfamiliar with Morava K theories, then you can really just keep this case in mind for the rest of the talk because it's already plenty interesting. V1 periodic homotopy theory is pretty cool already. Okay, so that's a spectrum of type N. It's just the first non-vanishing Morava K theory on it is the nth one, and I also need the notion of a Vn self-map of such a thing. So a Vn self-map, this is a map, say little v, from the suspension, some suspension of such a spectrum to itself, such that, well, it's like the Adams map in the following sense. If I look at the effect in the ith Morava K theory, then this should be an isomorphism in the nth one. It's an isomorphism if I is n and nilpotent. If you want, you can even arrange 0 by just taking an appropriate power of it if I is not n, okay? So just to drive home the point, like I'm just trying to systematize what I was saying before. So S0 is type 0 because its rational homology is non-trivial, and multiplication by p is a V0 map or a V0 self map, right? It induces an isomorphism in rational homology, and it turns out to be nilpotent in all the Morava K theories because they are of characteristic p. Well, the usual procedure is you take cofibers to get spectra of higher type. So this is a type 1. This is something that whose rational homology vanishes and whose mod PK theory doesn't vanish. And this Adams map that I had, let me just call it the Adams map, is a V1 map. Then once you have this, then it's not so difficult to see that the cofiber of this V1 map is of type 2. That's fine, but already now finding a V2 map on this thing is not so easy to do explicitly. I mean, it can be done, but there's actual work involved. Luckily, the fact that this systematic approach works, well, this relies on a couple of rather deep theorems. So the first one is a theorem of Mitchell that these type N complexes actually exist, which is not at all obvious from the definition. Okay, so type N finite spectra exist for all N. And Mitchell proved this by just giving an explicit construction of such a thing. And the other thing is these, well, Vn self-maps also exist. So this is essentially the periodicity theorem of Hopkins and Smith. So any finite spectrum of type N admits a Vn self-map. Okay, so these V1 self-maps you should think of as some kind of, as I said, sort of geometric incarnation of Bott periodicity. These higher Vn self-maps are, well, analogs of that, but not directly related to Bott periodicity. And also, maybe I should add to the statement of this theorem, these Vn self-maps, well, they're not unique, but they're unique in an appropriate sense. So Vn self-maps, I'd like to say, are asymptotically unique. Okay, so asymptotically unique, I just mean if you had two of them on the same spectrum and you suspend them, you iterate them often enough, at some point the iterates will become homotopic. So they're unique up to taking high enough powers. Okay. All right, so these type N complexes and these Vn self-maps, they exist, so we're allowed to use them. In these terms, I can define the general sort of Vn periodic homotopy groups in analogy with these V1 periodic homotopy groups that I had before. So let's fix V finite spectrum of type N, a little v, a Vn self-map of that spectrum. Then we define Vn inverse, oops, of pi star E with coefficients in this finite spectrum V to be the following thing. I mean, I can look at, I can either take the function spectrum or the space of maps, it doesn't really matter, from V to E take its homotopy groups. And now the point is, this little v will act by precomposition on the homotopy groups of this space. So again, the ring ZV acts on this, and I can invert that action. Like so. Okay, so the thing is, if you look at the left-hand side of this equation, there's no explicit reference of the map V, and that's okay, exactly because what I just said. This definition is independent of the choice of little v because of this asymptotic uniqueness. Okay, high enough powers are unique. All right. For n is 0, this will, like, the rational homotopy groups are like the V0 periodic homotopy groups, and I also defined these V1 periodic homotopy groups before, and this is the general form. Needs some more terminology. Sorry about all the definitions, but otherwise it's just hard to talk. So a map, a spectrum. So a map F from E to E prime is a Vn periodic equivalence if, well, it induces an isomorphism on these Vn periodic homotopy groups that I just defined. So if it induces an iso on Vn periodic homotopy groups. Now, the nice feature of this definition is that not only does it not depend on little v, it also doesn't depend on capital V. This is independent of the choice of capital V. And this, well, this is maybe not obvious, but this is essentially a consequence of the thick subcategory theorem, which I will not go into today. So again, maybe just quick examples. So a V0 periodic equivalence, that's just a different way of saying rational equivalence. And these V1 periodic equivalences, they also admit still a, well, maybe more familiar description. These are exactly the K-theory mod P equivalences, or isos. So maps inducing isomorphisms in K-theory mod P. So the first of these is kind of obvious if you unravel the definitions. The second of these is not so obvious. This is actually a theorem. So this, I guess, if P is 2, this is essentially due to Mohold, and it odd primes by Haynes-Miller. So there's some work going into this. This is not supposed to be clear. And also, like, an equality like this kind of breaks down when n is greater than 1, or at least we don't know. Okay, it's part of the telescope conjecture. All right, so what I want to do, I mean, I talked about rational homotopy theory in the first lecture, and there the game was to take homotopy theory and formally invert the rational equivalences. What I'd like to do now is formally invert the Vn periodic equivalences, to sort of zoom in on this part of homotopy theory that's sensitive to, that's seen by the Vn periodic homotopy groups. Right, so let me explain how exactly that goes. So I want to localize with respect to the Vn, periodic equivalences of spectra. Well, here's one way to say how that goes. What you can do is you define Tn. The notation is going to be a bit ambiguous here, but it will turn out not to matter. You define Tn to be, well, what's sometimes denoted as little v inverse of capital V. So here I'm assuming I fixed a type N spectrum, capital V, and a Vn self-map little v on it. So by definition, this is the mapping telescope. So this is the colimit along iterates of this little v, a homotopy colimit, if you will. Like so, okay, just formally invert this little v. So this is sometimes called the telescope. Then what I can do is I can regard this Tn as a homology theory, and I can look at the Bausfield localization with respect to this homology theory. So the Bausfield localization with respect to Tn, this is precisely the localization of stable homotopy theory of the category of spectra at the Vn periodic equivalences in the sense that I defined them. Okay, so this formally inverts the Vn periodic equivalences and only those. Okay, so all right, let me maybe say a little bit about chromatic filtration here. Standard notation in this subject is to write, I mean, what you can do is you can localize with respect to each of these Vn periodic homotopy groups. You could also localize with respect to the first bunch of them, like V0, V1, V2, up to Vn. So the standard notation for that here is lnf. So by definition, that's just a localization with respect to the sum of these guys up to n. So this is the localization with respect to, or here's one way to write it, VI periodic homotopy groups for I going from 0 up to n. It's maybe slightly informally formulated, but I hope it's sort of clear what I mean. What this gives is you get a tower of localizations for any spectrum. Get a whole bunch of them. The bottom one, so L0F, that's just fancy notation for the rationalization of E. And get one of these for every n. So you get a whole sequence of these localizations, and this sequence gives rise to a filtration on the homotopy groups of my spectrum by, well, let's say I look at the kernel in homotopy of each of these maps, and that is the chromatic filtration, or maybe you should call it the finite chromatic filtration on homotopy groups. I don't really want to get into the telescope conjecture here. So this defines the finite chromatic filtration on pi star E. Okay, this might seem a bit abstract right now, but this is really a very fundamental point of view for sort of modern day stable homotopy theory, and lots of interesting things have come out of this perspective. Okay, this is really a course about unstable homotopy theory though, so let me switch to spaces. So for spaces, I can really say many of the same things that I just said for spectra. So a finite pointed space V is of type n, well, precisely if its suspension spectrum is, right? So precisely if sigma infinity V is of type n. And similarly, I can talk about Vn self-maps of such spaces. It's just any self-map that once I take its suspension spectrum, it becomes a Vn self-map of spectra. So now you have to, well, the periodicity theorem will tell you that, well, any finite space of type n will admit a Vn self-map, possibly after suspending sufficiently many times. It's not true that any type n space actually has a Vn self-map. You might have to suspend a little bit. Okay, but after any finite number of suspensions, it will have one. So now I can also define for pointed spaces the Vn periodic homotopy groups. So we can similarly define Vn periodic homotopy groups by, well, the same procedure, right? I do something like, I look at the mapping space of pointed maps from V into my X. I take the homotopy groups and I invert the action of V1 on those. All right, so this is the same definition that I gave before. What I want to do is I want to take a slightly more structured perspective on this definition. So a slightly better way to phrase this definition, it's going to go as follows. So again, let's fix our capital V, and let's fix a VN self-map on this capital V. Then what I want to do is, using these two ingredients, define a certain functor from spaces to spectra so that the homotopy groups of this functor produce the Vn periodic homotopy groups of X. So in other words, I'm going to exhibit the Vn periodic homotopy groups of a space as the homotopy groups of some spectrum. Okay, so here's how that goes. We define what's called the telescopic functor associated to capital V. I should really say this is for n greater than 0. This will not apply for n is 0. That's capital Phi sub V. It's going to be a functor from pointed spaces to spectra. And I'm going to define it by just explicitly describing the constituent spaces of this spectrum, thinking of it as a sigma, as a pre-spectrum or whatever. Okay, so what I'm going to do, start at the bottom. I take this pointed, the space of pointed maps from V to X, and I define that to be V of X 0, the 0th space of this spectrum. And actually, I'm going to do the same thing for the dth space of this spectrum, and similarly, actually, for any multiple of D. So I take this space for any natural number K here. I'll take these as my constituent spaces. I mean, when specifying spectra, you only have to really specify them on a cofinal subset of the integer. So I've specified enough spaces, but I haven't specified any structure maps yet. So let me tell you how that goes. So the structure maps are exactly going to use this map little v. So the structure maps that I have to specify are maps of the following form. I look at this space in degree KD. We can go to the next one. So that will live in degree K plus 1D, and then I have to specify a map into the default loop space of this guy. So these are the types of maps I have to give. And well, as I was saying, we can use little v to do that, because if you think about it, here I could, well, this is loops D of that same mapping space. I could take the loops D inside, the cost of turning it into a sigma. So I can write this as sigma D Vx. Now it becomes clear what to do. Right here, you could just put precomposition by this map little v, okay? Now out of this data of this finite space capital V and this self-map little v, I've produced a spectrum. And now you can also see why n is 0 was somehow bad. Like for this to make sense, for this to actually be a spectrum, I do need D to be a non-zero. I mean, it has to be a positive natural number. It can't be 0. Okay, so all these Vn self-maps for n is not 0 will have this sort of positive degree here. So that's why this makes sense and actually defines a spectrum. Okay, so here's an observation about this construction. If you now compute the homotopy groups of this spectrum, E sub Vx, then you will exactly retrieve the definition of the V periodic homotopy groups. So this is V inverse map. I could even write Vn here. So again, this asymptotic uniqueness of the Vn self-maps will tell you that the choice of little v is not so relevant for this whole story. It's only about capital V. All right. But we can do even a bit better. I mean, now it's like we're doing homotopy groups with coefficients, where this capital V plays the role of the coefficients. Kind of want to get rid of those as well. So here's an even better way to look at this. There's a way to sort of put all these telescopic functors for all the various V into one functor. And that functor has a name. It's the Bausfield-Kuhn functor. Okay, so this is a functor that is usually denoted phi sub n. So it only depends on the height n that we're considering. And again, it's a functor that goes from pointed spaces to spectra, but it turns out to actually land in these Tn local spectra. So let me just have it land in there. So it has the following crucial properties. I'll tell you roughly how to build it in a second from the phi sub v's. So here, well, it has many interesting properties, but let me specify two for you. The first one is I can retrieve these sort of telescopic functors with coefficients in the way that, well, maybe you'd expect. You get it by taking, well, I can either write the function spectrum from V to phi n, but this is, of course, since V is finite, I could also write this as the Spanier-Whitehead dual of V smash phi n. So this reproduces all these other functors sort of with coefficients, and these, you know, this is natural in the appropriate sense in the spectrum V also. And the other property, which is, I guess, the original reason that this functor was considered so interesting, is that it does the following funny thing. What I can do is I could take this functor, it goes from pointed spaces to T and local spectra, and I can precompose it with a functor that goes from spectra to pointed spaces, namely loops infinity, right? So I could consider this composition of functors. And this is now a functor that goes from spectra to T and local spectra. And well, the property states that is actually the sort of the obvious functor from there to there. It's the Tn localization. All right. So this looks innocent, but this is actually somehow, it's not even like it's super difficult to prove. It's just hard to guess that such a thing might exist, because just having this is really a powerful device to prove all sorts of interesting results. So if you think about it, what is this actually telling you? It's telling you that the Tn localization of a spectrum only depends on its zeroth space. Okay, so of course, like Tn is something periodic, so it's not surprising that the Tn localization of a spectrum depends only on the connective cover of that spectrum. That's fine. But this thing here is only using the zeroth space as a space and doesn't in any way use the infinite loop space structure, right? If you give yourself an infinite loop space and you remember the infinite loop space structure, of course you can deloop it and build a connective spectrum. That's not what we're doing here. We're not using the infinite loop space structure in any way. So this gives you somehow a very strong, sort of unique delooping result for infinite loop spaces in Vn periodic homotopy theory. So somehow infinite loop space structures are unique in some sense, which is very much non-true integrally, right? That's just not the case. You could put different infinite loop space structures on the same space and get different spectra that way. Somehow this inverting Vn gets rid of that, which is kind of a magical fact. All right, so let me just quickly mention how the construction, how you're supposed to think the construction of this phi n. So the way this goes is as follows. So you use the following fact, which is a trick that I think is originally observed by Kuhn. So there exists a system, so, yeah, Kuhn. Let me write it like this: V1, V2, V3, etc. So a directed system of finite type n spectra with a map from the colimit to the sphere spectrum, which is sort of an optimal approximation of the sphere spectrum from the point of view of Tn homology. So this map, which is it's actually a Tm star equivalence for m greater than or equal to n. So for the nth telescope and all the higher ones, you can't see the difference between this colimit of type n spectra and the sphere spectrum. For the lower ones, of course, you do see a difference because this has no Ti homology for I less than n. And once, well, with this system in hand, you set phi n to be the inverse limit over the phi visa case. All right, so let me make this a bit more concrete at height 1, where it should be something at least somewhat familiar, because there it's really a story about mod p coefficients and p-adic coefficients, really. So here's the example. At height 1, the system of type 1 spectra that you could consider is the following one. You could take s minus 1 mod p, s minus 1 mod p squared, etc. And then there's a map from the colimit, which usually is noted s minus 1 mod p to the infinity, to s. This is like the map that, you know, sort of, in some sense, cones off to the top cell. At least that's what it does on each of the constituent pieces. And this map is an equivalence, well, clearly not rationally, but it's an equivalence after P completion. So it's sort of the best possible approximation of the sphere spectrum by P torsion spectra. Right, and this general system that we're just talking about is similar. It's the best possible approximation of the sphere spectrum by spectra that are, well, not only P torsion, but VI torsion for I less than N. Okay. Anyway. All right, so generally now people say, you know, the Vn periodic homotopy groups without coefficients are the homotopy groups of this functor phi n. And at n is 1, lots of calculations of this have been done. So won't be able to give a systematic survey of those, but well, of course, Mohold should be mentioned here, but there are many people that worked on this, like Thompson, Davis, Bousfield, and many more. But we really sort of understand these groups pretty well. Like the V1 periodic homotopy groups of things like spheres, or more generally spherically resolvable spaces, are well understood. So things like compact Lie groups, also Moore spaces, those are not spherically resolvable, but their homotopy groups are understood. Okay, so that's sort of a brief overview of what this Vn periodic stuff is about. What I want to do is look at what how this organizational principle interacts with, especially with the Goodwillie tower, which I was telling you about on Tuesday. So it turns out that interaction is actually, well, very striking in many ways. So let's quickly recall that when we looked at the Goodwillie tower, let me focus on the case where we do an odd sphere. So we talked about the Goodwillie tower of SL, the tower of spaces under SL, and I said the associated gradient of this tower, so the layers, the derivatives, are only interesting when you look in degrees of power of P. Okay, so really I can sort of run this tower a little quicker. I can go to P sub little p and then P squared, and etc. Okay, so there's a tower here. Where, well, I've indexed it like this because the only non-trivial layers are these dp to the k SL, so indexed by powers of P. Okay. So what you can do is you can take this whole tower, this whole resolution of the sphere, and just hit it with this Bousfield-Kuhn functor. Okay, so the good thing is this Bousfield-Kuhn functor turns out to preserve fiber sequences. Okay, so what I get a tower of spectra, sort of a resolution of this spectrum, if you will, phi n of SL, with, well, associated graded. So I just mean the successive fibers of the maps in the tower of the following form. Well, it's these dn's, which I could write as loops infinity of boldface dn of SL. So it's these derivatives we talked about last week. And then I can use this property that phi n essentially cancels loops infinity. Well, I have to localize. Oh, using n here is a terrible idea. Let's write this as P to the K. All right, P to the K. Okay. So you get a resolution of this, sort of the Vn periodic homotopy groups of this sphere in these terms, but at this point, well, it's not at all clear. I mean, I said phi n preserves fiber sequences. Phi n doesn't preserve arbitrary inverse limits or homotopy inverse limits. So it's not so clear that we're really retrieving the actual sphere. But that's where Aron and Mohold come in. So their paper is really the first sort of really key paper on how chromatic homotopy theory and the Goodwillie tower interact. It's really a beautiful paper. Highly recommend it. So they prove the following very useful things. Let me split this theorem in two parts. First of all, actually, if you look at this fixed height n, only at the Vn periodic homotopy groups, then all but finitely many of these layers are contractible. So we already saw that only the layers for powers of p are interesting, but it's even only finitely many that remain after inverting Vn. So let me write that down. So they prove that if you look at these layers that come up in this tower, then these are actually contractible. K is bigger than n. I mean, remember, I'm still talking about an odd sphere. For an even sphere, you have to essentially knock your coefficients up by a factor of 2, but the statement is very similar. And the other fact that they prove, so okay, so this tower, I mean, it looks finite in Vn periodic homotopy. It stops after the p to the kth stage, but that still doesn't mean that it converges. So that's not automatic. You really have to prove something here. But they do that. So they show that the tower converges in Vn periodic homotopy groups. So what do I mean by that? I mean that they prove that if you do phi n of SL, and you look at the map to the homotopy inverse limit of phi n of p to the k SL, and they prove that this is an equivalence. And by what I was saying in part 1, you can actually just identify this part over here as, well, as I said, this tower is finite. It just stops after the stage p to the n. Okay, so the Welsfeld-Kuhn functor on an odd sphere can be calculated in terms of this thing, which admits a finite resolution by infinite loop spaces, or well, after you've applied phi n, it admits a finite resolution by spectra of this form. Okay, all right. So that's a really nice result. So the upshot, let's write it down. You get a finite resolution of VNSL by spectra of the form that I had before, these guys. As I said, these are spectra that we know something about. All right, so I'm not going to explain the proof, but let me just say the crucial ingredient of the proof somehow is their calculation of the cohomology of the layers that I mentioned last time. So what they show is actually that the FP cohomology of these layers, dp to the k SL, is free over an appropriate subalgebra of the Steenrod algebra. So I prove that this is free over subalgebra that's usually denoted A star k minus 1. So at the prime 2, this is the subalgebra generated by all the square 2 to the i's, where I is at most k minus 1. Okay, so they just do this by a detailed sort of cohomological analysis of these layers, and then somehow the point about something like this, like there's some homological algebra that is often used in chromatic homotopy theory, which dates back quite a bit. I guess it's Anderson-Davis at p is 2 and Miller-Wilkerson at odd primes, that tells you that if you have a spectrum with this sort of freeness property for its cohomology, then you get vanishing lines at certain slopes in the atom spectral sequence for such a spectrum. And so these vanishing lines, depending on, if k gets higher, the slope of the vanishing line gets lower. And this will allow you to prove things like this, like that once you invert Vn, the thing must be contractible because Vn acted by an element of higher slope than the vanishing line, these kinds of things. And then the fact that you actually have quite good control over these vanishing lines is also what allows you to prove this. So you look at the vanishing lines for the atom spectral sequences for all these layers, and then somehow you can argue that there can be no annoying sort of Vn torsion in all the layer families building up to an actual Vn tower in the limit, et cetera, et cetera. But these are all vanishing line arguments building on this fundamental observation. So that's really the key step, the key thing they observed. Okay. All right. So so that's a great result. It sort of tells you where you want to look when you're calculating these VN periodic homotopy groups of spheres. What I'd like to do now is tell you how you can actually try to start attacking this calculation along the lines of the results of Behrens and Resk. So essentially what they do is well, let me tell you what they do. Let me explain this sort of by analogy with how I was explaining rational homotopy groups in the very first lecture. So recall that in rational homotopy theory, we could extract the rational homotopy groups of a space, or maybe they're duals. So they're linear duals, essentially from the cochain algebra of the space. So from the way I phrased it in the first lecture was you could take the derived indecomposables of cochains of X with coefficients in Q, or maybe I should really say some CDGA model of it. For example, Sullivan's polynomial forms, or piecewise linear forms. Okay, so this principle has an analog in VN periodic homotopy theory. And this is really something that was identified by Behrens and Resk. So let me try to explain how it goes. Well, essentially, I just have to take the ingredients from rational homotopy theory and generalize them appropriately. So what I'll do is, well, I have to first talk about the analog of derived indecomposables. So this is what goes under the name of topological Andre-Quellin homology. So I'll use this notation here for the homotopy theory of augmented commutative ring spectra. Okay, so these are ring spectra that have an augmentation to the sphere spectrum, and well, there's an adjoint pair that relates this category to spectra. Well, there are several, but I want to focus on a specific one. So what I can do is, if I give you a spectrum, I can build an augmented ring spectrum by taking the trivial square zero extension. So this functor here is the functor that takes a spectrum, say M, and sends it to, let me just write it informally, as S plus M, where I'm thinking of this as a trivial square zero extension. It's something you can do in algebra. There's a version of this in higher algebra as well. And this functor has a left adjoint. I think Doug likes me to use this symbol, wants me to use this symbol, so I will. So the top one is the left adjoint, and this has a name. This is what's called TAQ. So this is really the form of derived indecomposables that I want to think about. Maybe one remark about this adjunction. There's a nice way to characterize this adjunction by universal properties. So this adjunction actually exhibits, I guess this is originally an idea of Bestera and Mandel. This exhibits spectra as the stabilization of augmented commutative algebras. So a different way to paraphrase this observation is that TAQ is the universal homology theory for augmented ring spectra. Okay. So in the same way that usual singular homology allows you to, in some sense, study the cell structure of a space, TAQ is what allows you to study the cell structure of an E-infinity algebra, a commutative ring spectrum, where cell structure now means, well, the way it's built out of free E-infinity algebras on cells, on spheres, shifts of spheres. All right. Okay, good. So, well, I only gave the abstract perspective. I mean, you can write an explicit formula for TAQ in terms of bar constructions, which in the interest of time, I will not write down. What do Behrens and Resk do? What they show is that you can compare the Bausfield-Kuhn functor to TAQ of the cochains on your space, where cochains you have to interpret in the sense of spectra, in the sense of ring spectra. So let me state this somewhat precisely. Let's take a pointed space, which is a finite CW complex, finitely many cells. What they do is they build a natural comparison map. That's the term they use. Going from the nth Bausfield-Kuhn functor on X to the following construction. All right, so let me write this down in order. So what I can do is, given X, I can look at, well, S to the X plus, or the Spanier-Whitehead dual of X. So this is the function spectrum from sigma infinity plus of X into the sphere. This is a commutative ring spectrum, right? And well, you can think of it as some version of the cochains on X. It's cochains with values in the sphere spectrum. So this is an augmented ring over the sphere spectrum. The inclusion of the base point gives an augmentation. I can take TAQ of it. Okay, so I can take the indecomposables of this ring spectrum. I can take the dual of that and TN localize this whole thing. I mean, okay, in the paper of Behrens-Resk, they look at KN rather than TN localization, but the same principle applies. This also works. So they construct this map, first of all, which is a bit like what happens in rational homotopy theory. It compares, in this case, it compares the VN periodic homotopy groups to the, well, let's say the derived indecomposables, or the linear dual of the derived indecomposables of the cochains on X, appropriately localized. So, well, that's one thing. They construct this map. What's much more important, they show that it's an equivalence in good cases. So this map is an equivalence when X is a sphere. Right. So what actually happens is they show that for general X, what this map really does is it identifies the Goodwillie tower, or phi n applied to the Goodwillie tower on this side, with a certain natural filtration of TAQ, which is called the Kuhn filtration. And then to get the result that it's actually an equivalence in sort of the limit of those towers, you need a convergence result. So you need to know that the Bausfield-Kuhn functor commuted with the limit of the Goodwillie tower, which is okay when X is a sphere by this result of Aron and Mahold. But in general, it's unclear when you can or cannot do that. The limiting procedure always works out on this side, by the way. So this has this filtration on that side is always good. So the upshot of this is that you can really try to calculate phi n x by understanding the cell structure of the commutative ring spectrum. This guy, or maybe it's TN localization. So in other words, how is this thing built from free commutative ring spectrum? Right. So this might seem hard, but if you're doing this at height 1, these really are approachable things. You can really do this. Like if you go back and look at Bausfield's calculations of V1 periodic homotopy groups, he doesn't say it in these words, but what he's doing is really this procedure. He looks at the K-theory of your space, looks at how you can resolve the K-theory by sort of free things, free in the sense of K-theory, so free algebras with Adams operations, and then uses those resolutions to calculate this. So it's really this Behrens-Resk procedure in disguise at height 1. So Jens Kjær recently wrote a paper where he sort of carefully compares what Behrens-Resk do to what Bausfield does at height 1, where you can see this principle in action. Okay. All right. So yeah, I guess we have a few more minutes. Oh, I've been an idiot. I skipped a really, really crucial example, which I'll mention now. It's a little out of order. I should have said this before, but a really crucial example of the Aron-Mohold theorem, which I could have told you about before going into this Behrens-Resk thing. At height 1, I can apply it to something I told you last week. So this Snaith map that we looked at. So this was a map, well, that compared an odd sphere or a loop space of an odd sphere to Q of a real projective space. The Snaith map induces an equivalence at the prime P is 2 from the first Bausfield-Kuhn functor on an odd sphere to, well, that real projective space that we had. So I should write the localization of sigma 2L plus 1 RP 2L. Okay, so this is really, this was already proved by Mohold in his image of J paper. So this is an older result of Mohold, but it can be sort of re-understood, re-proved through this Aron-Mohold theorem. So this is a map that we talked about quite a lot on Tuesday. And you can apply this Goodwillie perspective in this Aron-Mohold result to see that this Bausfield-Kuhn functor in this height 1 case has a very explicit description in terms of this spectrum. I really mean the suspension spectrum of RP2L over here. And this is something you can really compute with, right? Mohold completely computes the homotopy groups. Like everything is known here in terms of homotopy groups. Okay. What I would also like to do is show you a short example of such a calculation by Bausfield, which is essentially this example at an odd prime, but also maybe we can do that in the discussion session afterwards if anyone wants to see that. What I'd like to finish with is a short comment on Lie algebra structures. Those were present in rational homotopy theory, and they're present here as well. So the key point, which I already mentioned last time briefly, is that these spectra, these derivatives of the identity that come up in studying the Goodwillie tower. So this is a priori a symmetric sequence of spectra. They have, the nth one has an action of the nth symmetric group. These naturally form an operat. So this operat structure was identified by Michael Ching. And this operat really deserves to be called the spectral Lie operat. So it's the version of the Lie operat in stable homotopy theory. Well, I already mentioned this also last time, if you take its homology, you would reproduce the ordinary Lie operat. So sort of this principle of Cazul duality that I also mentioned in the first lecture applies here as well, not only in rational homotopy theory. And I will tell you that if you take TAQ of an augmented ring R, you dualize it, then this is a spectral Lie algebra. It has a natural spectral Lie algebra structure. In the same way that we had this adjunction between Lie algebras and commutative algebras in lecture 1. So this allows for maybe a refinement of the statement that I made of the Behrens-Resk results. So the first thing is that there exists a factorization of the Bausfield-Kuhn functor. This Bausfield-Kuhn functor goes into Tn local spectra, and you can actually factor it through Lie algebras in Tn local spectra in a certain natural way, in such a way that the Lie algebra structure, or the spectral Lie algebra structure, reproduces the Whitehead bracket on the homotopy groups. This reproduces the Whitehead bracket on Bn periodic homotopy groups. And the other thing is that the comparison map, so this phi nx to the dual of TAQ is a map of Lie algebras, spectral Lie algebras. Okay, so this is really the start of a story where you can start working with these things, these phi n of x's, as if they were Lie algebras. Well, they are in the appropriate sense of stable homotopy theory, and really start computing with these things. So various people over the last few years have studied the structure of these Lie algebras from a calculational perspective. So they have homology operations similar to Dirac-Lashoff operations for commutative ring spectra. And well, these operations are understood for at least F2 homology. So that's where Behrens started, and then Omar Antolin Camarena worked that out in his thesis. And then, for example, Lucas Brantner worked out these things in E theory. And you can really get your hands on some nice calculations that way. I'm out of time, so I'll just leave it at that.
Okay.